Hi, I'm Scott Knockleby. In this video, we're going to look at the 6 problems of robot kinematics. By the end of this video, you should be able to classify the 6 kinematic problems of robot manipulators. As well, you should be able to identify the joint space and task space variables associated with robot manipulators. So we're going to look at an example to illustrate the 6 problems. And in this example, we're using the planar 3R manipulator. So 3R, what does that mean? Well, the R stands for revolute in this case, so we have 3 revolute joints. All right, planar, so it's a manipulator operating in the plane, which differs from a spatial robot that operates in 3D space. So we have a base, we have link 1, which length is denoted by the L1. We have link 2, whose length is denoted by L2, and link 3, whose length is denoted by L3. And then our robot will have a tool, or what we often call an end effector in robotics. And we often just abbreviate that EE. So this is a 3-link revolute jointed planar manipulator. Now, when we're talking about robotics, there are what we call joint space variables. And task space variables associated. All right, and so we're going to look at these for the different problems. So the variables depend on the problem we're looking at. So in terms of displacement, if we define vector x here, it's comprised of our x position, y position, and our angle, all right, of our end effector. So these are the task space coordinates, or variables. So if we go back to our robot here, let's draw in a reference frame. So this will be our y-axis, and this will be our x-axis. Our position of our end effector, this is be our x coordinate. All right, this would be our y coordinate. All right, and then the angle of our tool measured relative to the horizontal, we define that as alpha. So we have x, y, and alpha. Those are our task space variables, and they define the pose of our end effector, which means the position and orientation of our end effector. Now, in terms of joint space variables, in this case, this deals with the joint angles for our robot. So we can define vector q, which will be comprised of theta 1, theta 2, and theta 3. All right, and these are our joint space variables. So if we go back to our robot here, that would be theta 1. It's the angle of link 1. Link 2 now, we're not going to measure it relative to the horizontal. All right, we're going to measure it relative to link 1. And the reason we do this is to make the derivation of our kinematics easier. So this would be theta 2. And we do the same. This will be theta 3 relative to link 2. All right, and so those are our joint space variables for the displacement problem. All right, so if we were given theta 1, theta 2, and theta 3, we could then probably calculate x, y, and alpha. All right, we'll talk about that more in a few minutes. Now, in terms of velocity, the velocity is just simply the time derivative of these two equations above. Okay, so it'd be x dot, vector x dot, which would be our translational velocity in the x, our translational velocity in the y, and then our angular velocity of our end effector. Okay. We would have q dot, which are our joint rates, all right, which would be in this case theta 1 dot, theta 2 dot, and theta 3 dot. All right, so we again have our task space variables. In this case, it's x dot, y dot, and alpha dot for the velocity problem. And we have our joint space variables, which are theta 1 dot, theta 2 dot, and theta 3 dot. So our last set of variables concern the static force problem. So in the terms of the static force problem, we're going to have a wrench applied by our end effector, which is comprised of a force and a moment about the z-axis. So in terms of our task space variables, we'll have f, which is fx, fy, and we'll have our moment, which for the planar case is just mz. All right, and they specify a wrench quantity in the task space. Okay. In terms of the joint space, we're interested in the torques that are required to apply that wrench. So we'd have tau 1, we'd have tau 2, and we have tau 3. All right, so tau 1, tau 2, and tau 3, they are our joint space coordinates. So tau would equal tau 1, tau 2, and tau 3. All right, and these are our torques. And you can think of them as the force coordinates in joint space. So when we're talking about our robot kinematic problems, forward and inverse are used to label the direction of the problem. So in terms of a forward problem, this is where we'll be given the joint space variables, and we're trying to figure out the task space. So let's go to our example here. So if we're talking about, say, the forward displacement problem, I would be given theta 1, theta 2, and theta 3. And from it, I want to calculate the position and orientation of our end effector, which would be x, y, and alpha. Okay. The inverse of this is we would be given our task space variables. And then from it, we want to calculate our joint space. So again, if we look at our example, so in this case, suppose we're given the pose of our end effector, so we're given its position and orientation. We'd want to calculate what are theta 1, theta 2, and theta 3 to give us that position. All right, and so often in robot kinematics, the inverse problems are a little more tricky than the forward problems, as you'll see in subsequent videos. So defining forward and inverse and our joint and task space variables, we can define the 6 problems of robot kinematics, which are forward and inverse displacement, and we'll often abbreviate these as FD and ID. We have forward and inverse velocity, FV and IV, and we have forward force and inverse force. And it's important to note that here, when we talk about in terms of kinematics problems, we're talking about the static force problem. All right, dynamics forces will be in a different module. Okay, and so in this case, we have our forward force and our inverse force, or FF and IF. So in the next series of videos, we're going to look at examples of each of these problems for that 3R planar robot.